This video is going to be about evaluating logs or exponents using log or exponent properties, or even doing it the long way and just rewriting logs as exponents and back and forth. So the first two I have on here are similar to questions 10 and 11 on your test review. They are actually using a property that you could memorize, but I'm going to show you how you can evaluate it the long way, just in case you forget the property that you can use from our notes. So this first one, we are trying to evaluate what this is equal to. But right off the top of my head, I don't know what the log of 50 is equal to. In fact, it's not a whole number because 10 is the base. And if we just looked at just for a second what log of 50 is, we're asking ourselves what power of 10 gives us 50, and that's not going to be a whole number. So this is really not friendly if we just look at it that way. Instead, what I want to do is let's try and rewrite this as a log, since we can't evaluate it as an exponent. That's always a good option. Now, just like I said in the previous video, if you haven't watched it, go check it out. If you want to rewrite an exponential expression, which this is, even though this has a log as an exponent, this is a base and an exponent, so it is an exponential expression. If you want to rewrite it as a log, you have to look at a couple of things. First, the base of the exponential is the base of the log. So if we were going to rewrite this, it would be a log base 10. Then the answer for the exponential, which is the output, becomes the input for the log. So that x is going to go inside. And then the input for the exponential, which is the exponent, becomes the output, or what that log is equal to. Now, I did mention briefly in the previous video as well that if there's a log with no base written on there, you can assume that it's a base of 10. If it was a natural log with no base, then that would be a base of e. So this is also a base of 10. Now, if you look at these two sides, and we're claiming that this log is equal to this log, and everything about this log is identical to this one, except for that input, then we can assume that the inputs are also identical. They match physically. So this x is the same thing as 50, which means that we were able to identify that the original expression all along was just equal to 50. Now, there is a shortcut way to do this, of course. If the base of the exponent is exactly the same as the base of the log in its power, then you can assume that the inside of that log is what this whole thing is equal to. So in this case, I can use that shortcut over here because the base of the exponent and the base of the log match. So I'm going to assume that this is 15. But as usual, I want to prove that that's true to you, so you don't just assume it. If we rewrite this one the same way we did over here, this started out as an exponential, so we're going to rewrite it as a log. The base is 3. Then what the exponential was equal to, which in this case was an x since I didn't know that it was 15, that's going to go inside. And then the exponent, the actual power from the original problem, is what the log is equal to. And here you can see again we have identical logs, so the inputs must be identical for them to be equal, which means that x was 15. So now I also want to look at these other problems like numbers 12 through 14, where sometimes you can use some of the log powers for contracting logs into one term, and sometimes you can't. In this case, I could for 2 of these terms, but not for all of them, so there's got to be something else here. One thing that you could do if you want to is actually try and combine the logs that do have the same base. Remember, those properties for combining logs only work if they have the same base. So in this case, if I wanted to, I could combine those two together, and that would create a log base 4 of 4 divided by 8, 1/2. But I still can't combine these two logs together because they have different bases. And so I still need to figure out a way to evaluate these anyway without using the property. So from here I can continue by evaluating each individual log and then adding them together. Another option that I have is from the very beginning. Instead of starting by combining these two logs, I could see if I can evaluate each one individually. In this case I can. This log over here, just looking at it off to the side, log base 4 of 4 equals something. If you can't imagine what that x could be, you can rewrite it as an exponential. So the base is 4, and then the output becomes the input, and the input becomes the output. So again, we're kind of looking at the same thing we were above. If the two sides are identical and they must be equal, then the powers must also be identical. So x in this case, or that log base 4 of 4, is just equal to 1. Then we move on to the next log. Log base 3 of 27 is equal to something. Rewriting it as an exponential, 3 to the power of 3 is what's equal to 27. So I know that that entire log was originally equal to 3. And then finally, log base 4 of 8 equals something. Rewriting this as an exponential. All right, we're running into a problem. This time, there's not an obvious answer to this. 4 to the first power is 4. 4 to the second power is 16. It skipped right over 8. So we're going way back to the very first lesson where we were solving these equations by changing the base to something that they both share. Well, 2 to the power of 2 is 4, and 2 to the power of 3 is 8, so I can change both sides to have a base of 2. 2 squared is equal to 4. 2 cubed is equal to 8, and then that 4 had a power of x on it. Now when you have a power of a power, you multiply those, so this would turn into 2x equals, or 2 to the 2x equals 2 to the third power. And now since those bases match, we can assume that their powers also match. So in this case, x would be 3 over 2. That was a lot of work, but it got us that final result. So this was equal to 3 over 2. Now when I evaluate this across, that's 4 minus 1.5. Five over 2 would be our final answer. Let's see if we get the same thing by doing this way. Over here, I've got log base 4 of 1/2. So 4 to the power of x equals 1 over 2. Again, they don't have the same base, but I can make them both a base of 2. So I'd get x equals negative 1/2. And then 3 to the power of 3 is 27. And that also would come out to be 5 over 2. So either way, we get the same result. Whether you combine the two with the same base first or not. That one did have fewer steps because we had fewer logs to evaluate, but it's all a preference. You may also want to keep in mind that sometimes when you combine logs, you may get a number that's harder to evaluate. Like this one was really simple, so I like to keep it there. Or sometimes it's really difficult to evaluate them when you keep them apart, so it may be beneficial to put them together. Keep in mind that you have options for all of these, but the process is the same. You're evaluating each log individually, replacing it with what it's equal to, and then solving using those whole numbers that you get. And that gives you your final result.